Yeah, welcome to the 13th lecture, an introduction to the lattice Boltzmann method. We are coming to the end of this semester, and today we'll have a kind of an advanced topic, not because the model we are looking at is very advanced, but because of what we are actually doing with it, namely in this course, you should have learned most of the tools that you need to actually develop new lattice Boltzmann models. And this is what we are going to do on a pretty simple example, of course, because we want to do it in a single lecture. Yeah? Okay, so the challenge that we set us is we want to derive a lattice Boltzmann method for the diffusion equation in 2D without any advections. Just this usual fixed law that there is a density C that changes in time according to a second spatial derivative in C. So this is the Laplace operator, and there's the diffusion coefficient D. And now the two challenges that we set us are, let's A, do it as simple as possible, and B, do it as accurate as possible. And I notice, of course, that doing it as accurate as possible has no end. Yeah, let's just do it as accurate as possible as we can do it in, say, this one lecture, okay? And in this one lecture, and with this standard discretization that we have also be using the D2Q9 lattice. So the starting point for us to build a model is to recall the asymptotic expansion that we have addressed in lecture 6, and we'll call this the equation 13.1. So this is a repetition. The asymptotic expansion of this lattice Boltzmann model in 2 dimensions, yeah, leads to the case that we have a sum over mn, L, and q starting from 0, all of them going to infinity, over m factorial, n factorial, L factorial. Here comes the smallness parameter epsilon to m plus n plus L plus q divided by 2 by the power of m plus n plus L not plus q. And then the derivatives, dt, the mth derivative in t, the nth derivative in x, and the lth derivative in y. And of course, this equation is too long for one line, so I will continue in the next line. Probably, I hope that the next line will be enough. So this acts, so the derivative acts on m, a plus n, the moment, and this is to the order q, and it has the second index b plus L, and this goes into 1 minus 1 n plus L plus m minus omega a plus n b plus L, and this is an omega to the order of q, this divided by 2, and this goes into 1 plus, so the difference here is 1 minus 1 plus, minus 1 n plus L plus m, n plus L plus m, right. So this kind of looks horrific. I remind you that this comes out of the Taylor expansion of the lattice Boltzmann equation. From Taylor expanding. the lattice Boltzmann equation. So the lattice Boltzmann equation, here's the post-collision distribution Fij at the position x minus Eij delta x half and t minus delta t half is, or let's say, better we write it this way, minus Fij, so this is the pre-collision, x now plus Eij delta x half and t plus delta t half, and this together is equal to 0. So we'll Taylor expand this using, in addition, that this Eij is the vector Ij, and delta t is proportional to delta x square, and this is proportional to epsilon square, so this is in diffusive scaling. Okay, Taylor expanding this and taking the moments leads to this big equation that we need to actually derive lattice Boltzmann methods. So we have interpreted this in previous lectures, now we are just going to use it, yeah, accepting it the way it is. So, I mean, in addition to Taylor expanding, we also have the asymptotic expansion of the moments, here indicated by the Qs. Okay, we will combine this with the relaxation time ansatz. And since our first challenge is to make it as simple as possible, we'll start with BGK, single relaxation time ansatz. So, and then we have this moments MAB in post-collision, so they are now not expanded, is MAB before collision plus the single relaxation parameter omega into MAB, their equilibrium, minus the pre-collision state. And then we also define this omega AB as the collision term, which we define as the, very simple, the post-collision moment minus the pre-collision moment. Yeah, so obviously the difference between them is the collision. And then we do the change of variables from the pre-collision state, MAB, to an intermediate state, MAB with this overbar, minus, what am I saying? Yes, right. Minus half the collision. So we take, so to speak, the MAB overbar is the moment in the middle of the collision, so we take half of the collision away, so that we come to the pre-collision, and equally, the post-collision is the moment in the middle during the collision plus 1/2 the collision. So this allows us to write this equation up here, that we have up here, this one, as MAB over in the middle of the collision plus omega AB half is equal to MAB bar minus MAB, not MAB, omega AB half plus small omega, so that's the relaxation rate, MAB equilibrium, so this is non-modified, minus MAB bar. So here we have to subtract subtract the collision operator, and because we have a minus in front of it, we write it with omega, with plus omega AB. So, okay, this is this modification, and now we want to see what this means in terms of MAB. So, see, obviously, this here goes away, but it's not, but it remains to be here, right? So, if we solve for this guy back here, we get that MAB over bar is equal to MAB equilibrium minus 1 over omega minus 1/2 omega AB. So this is this modification. And now for simplification, we'll call this term here tau. Yeah, so this is, I mean, there may be some confusion out there in the lattice Boltzmann world how tau is defined, because it's defined in different ways. So sometimes it's defined as 1 over omega is equal to tau, but that tau is a numerical parameter, not a physical parameter. The mean free time between collisions, this tau is actually 1 over omega minus 1/2. So you need to have this 1 over this minus 1/2 in it to have actually the physical correct definition of the mean free time between collisions. Yeah, even though it's sometimes used differently. And also I have to admit the definition of f over bar and f without over bar is not consistent in all literature, and I have been accused of doing it wrong, yeah, because I use my definition where the situation in the middle of the collision is the f over bar, which is actually, from the Boltzmann perspective, the correct f. So, because it's the correct f, some people say it should be f without over bar, and we should call the pre-collision state f with over bar. Okay? I understand this logic. I've used a different nomenclature all the way along, so I stick with my nomenclature here. But you have to be aware that it's not everywhere the same. Okay, now this is standard. Now we want to build our model, and for building our model, we have to make a decision on how we define our variable that we want to solve for, to which moment do we associate this. So we have to make a choice here, and the choice is not necessarily unique. So we choose the conserved quantity, and also we have to choose its asymptotic order. This is also not unique. So what we choose here is we say that M00 to the zeroth order could have a different choice, but we choose to the zeroth order. This is supposed to be our C, so this the quantity for which we want to solve the equation. Okay, now this is the choice, and now we have to build a model using our knowledge on the asymptotic behavior of the Boltzmann lattice Boltzmann equation. For this, we first recognize that we can write this equation 13.1 in a recursive way. Now this will help us at least a little bit. So we write this in recursive form so that we come to the recursive asymptotic analysis. While doing this, we are going to build in we build the BGK collision already into the equation by replacing MAB over bar MAB minus tau omega AB. So this will simplify. Actually, let me see. We had. I think I have to do it the other way around. Right? This was MAB. So it must be. Let me briefly think. We get yes. So it's the other way around. Yeah, I miswrote this. I guess. Yeah. No. Wait. I've even missed. No. Sorry. It is. What did I do? Okay, now I really miswrote it. Yeah, so what we have above here. Yeah, MAB. Yeah, so well, first of all, we have to restate the MAB without overbar in terms of the overbar, and then we have to restate this again with the collision operator, the equilibrium minus tau omega AB. We can do this in the very end, but then it becomes much more difficult. So it's a good place to introduce this, but we also have to keep in mind when we do this in this point, we've already decided that we do BGK, right? Yeah. Okay. So what we are now going to do is we now do this we try to restate this here to give us the leading term of this equation 13.1. So the leading term is MNL, so everything is 0, and this goes to 0. That would be the leading term of this equation, right? And we introduce the other things here. So let's just write MNLL epsilon by the power of MN plus L plus Q. So they all will be 0. Divided by 2, M plus N plus L comes dt M dx N dy L M. So now we have here made the replacements. Did we make the replacements? No, I haven't. Okay, it doesn't matter. M A N plus B L to the order Q, 1 minus 1 N plus L plus M minus omega A plus N B plus L, this to the order Q, and this 1/2, and 1 plus minus 1 N plus L plus M. And if we evaluate this, yeah, because it's the sum only going to 0, well, what we are going to have is minus omega AB to the order Q epsilon Q. So this is the 0 part. And now we rewrite this equation 13.1 in terms in recursive parts, in recursive ways, what we do, because it is the entire equation is supposed to go to 0. We say that omega AB at the order k is omega AB at the order k. So now obviously this will cancel out, yeah, because the equation 13.1 equals to 0, right? So we put it on both sides. Then we want to isolate a specific order. This is, and the order that we are asking for is the order k. So I'll divide by epsilon by the power of k, yeah, the epsilon, and then I multiply the entire thing with the sum. And now let's be careful on how to write the sums. We have the sum over m, n, l, and q equal to 0, and 2m plus n plus l plus q is equal to k, okay? So I'm not writing an upper bound here, yeah? So the idea is, maybe I could write this in a mathematically more accurate way, but the idea here is that we count over all m, n, l, q starting from 0 with the constraint that 2m plus n plus l plus q is always k. Yeah, so this is the constraint here. And this, again, is the same equation, is m factorial, n factorial, l factorial, epsilon 2m plus n plus l plus q. And now what you see is, because 2m plus n plus l plus q, yeah, is k, yeah, this will eliminate all the epsilons from this equation. Yeah, that's the idea. Divided by 2m plus n plus l. And now comes the derivative, dt m dx n dyl. This is supposed to be an L. And here comes m. All right, so what we do here, so sorry that I wanted to do this previously, but I've not written it in the last equation. We put in here the equilibrium, yeah, minus, so we replace m over bar by m minus the m equilibrium minus tau times the collision term, right? So q a plus n and b plus n, and all of this goes into 1 minus 1 n plus l plus m. And then there is still the other collision term left, a plus n plus b plus l, and this is to the order q, of course. 1/2, 1 plus minus 1 n plus l plus m. So, in a way, you could say this looks very horrific. Now, the thing is the following. You can automate this, obviously, yeah? Now, with this, you can compute what the omega AB is, so you get an equation for an omega AB. So you're at a given k, yeah. So you can program this, and you ask the computer what is omega AB to the order of k. So then the computer will tell you that this is a function of the equilibrium moments, okay, and omega AB to another order, right? And then you can ask, what is that? Yeah, and so you come recursively forward, and this, therefore, this is a recursive asymptotic expansion here, or asymptotic or you can do a recursive asymptotic analysis with this equation. Yeah. So first of all, here we do what we often do in numerics. We are equating coefficients and say that because epsilon is defined to be larger than 0, but otherwise arbitrary, how many R has arbitrary? And omega A, B, K, so that's an important thing to remember. These things, by definition, are not dependent on epsilon. So we outsourced all the dependency in epsilon into this expansion of them. So they must not depend on epsilon. And therefore, we have to restrict the sum to terms of order epsilon by the power of k. Yeah? So what is on the left side, yeah, must have the same order in epsilon as what is on the right side. And we ask for something at a specific order, so it can only be that specific order. Basically, so this is equating coefficients is the trick where we actually have a series, yeah, so a sum over infinitely many terms, and we put this into a sequence. Yeah, where we can look at each order individually. Yeah, this is the idea here. So we no longer have to sum to infinity, but we now have a fixed amount of terms that we have to consider. So what I just said is that this equation 13.2 is a recursive equation where obviously omega AB, to some k, or of order k, depends on some omega A plus n and B plus L to some other order Q. And now the thing is that since in this equation here, Q is always smaller than K in 13.2, the recursion will converge. So you start with K10, yeah? So K10 only depends on Q's smaller than 10, yeah? And they only go down to 0, and there's nothing negative, and so it ends here. And so we have a guarantee that all of this will converge, and we have a finite system. However, that things are finite does not mean that they are small. So the result of the recursion can in fact be very large. And the advantage that we have is that our system is so structured that we can relatively easily put it into a computer algebra system, yeah? Then it may be a little bit difficult to see what actually happens, but usually most of the time computer algebra systems give the correct answer. Okay, let's get started, because in the beginning it's actually not so complicated. We are applying equation 13.1 to the zero moment, zero order moment. This means we put A as equal to 0, B equal to 0, and we also put K, the order, equal to 0. And this will result in omega 0, 0. 0 is equal to omega 0, 0. So we said we put them on both sides. And from the equation itself, we get omega 0, 0, 0, which means that all of this is 0. Okay? So we see that to the 0 order, it is 0. Yeah? Okay, this is not wrong. Yeah? So let's step up. We say k equal to 1. So omega 0, 0, 1 is omega 0, 0, 1 minus omega 0, 0, 1. Now, our equation counts up, so always remember these indices. Yeah, so we have in order 1. Yeah, so we get the first derivative in x. Yeah, so this is order 1. Yeah, so we get one derivative in x of the moment m1. Yeah, because we count up the first index with the derivative. So 1, 0, and because we counted this up, this here must be 0. Yeah, so this moment must be 0, because the additional order comes from the derivative. So in order for this to be first order, the moment itself must be 0 order. Yeah, minus tau omega 1, 0, and this again to order 0, plus dy m 0, 1 equilibrium 0 minus tau omega 0, 1, 0. Okay, question. What's about time derivative? Do we have a time derivative? No. Why not? Okay, the answer was correct, but no reason. Well, the time derivative costs, the time was what we used the index m with, yeah? And m, epsilon by the power of 2m. So we are in diffusive scaling, so one time derivative costs us 2 orders. And we have only 1. So this would lead to a moment of the order of -1, and the moment of order -1 does not exist, so there's no time derivative. So we are actually finished here. Yeah? In a sense, we are finished here, but we have to deal with the recursion, yeah, because we have here omega 1, 1, 0. So we put in the recursion, so and say this, what we need is omega 1, 0 to the order 0, and this is by the same token as it was here. Yeah, so we'll have no time derivative here, and no spatial derivatives here, and no time derivatives here, because we are to the order 0. So we'll end up with this minus 1, 0, which this will cancel out, meaning that this here is 0, and though it will disappear here. And of course, this by analogy will mean that this here is also 0. So this leads to the partial differential equation. Omega 0, 0 to first order is equal to dx m 10 equilibrium to zero order plus dy m01 equilibrium to zero order. And well, this looks a little bit like a differential equation, but it's not the one that we want, because we want something with time in it. Yeah. So this is not yet what we want. Okay, so we'll go on. We go on by taking the next order, omega 002. This is omega 002 minus omega 002. And now, again, the same thing. We lose by one spatial derivative, we lose one order. So this comes now in the moment M10 equilibrium to first order, so that together they are second order, right? Minus tau omega 10 to first order. The same thing in the y direction, 0, 1 equilibrium first order minus tau omega 0, 1 first order. And now we actually have the time derivative, because in the time derivative we lose two orders. Yeah? So dt comes now m00, because in the time derivative we do not count the indices up. It's the same moment, and it's equilibrium to zero order minus tau omega 00 to zeroth order, of which we already know that it is 0. So from this we know that it is 0, but for the other two we don't know what they are 0. So what we're going to do is we use recursion again. Use recursion again and ask what is omega 10 to first order now. This must be omega 10 to first order minus omega 10 to first order plus dx. Now comes m20 equilibrium, obviously which order? 0 minus tau omega 20 to 0 order plus dy m. So what moment? 0, 2. So we start with A. So what is this? This is A equal to 1, B equal to 0. Yeah? And then what do we do with the moments? We are counting up. Now this is the second index. We are counting up the second index.
Yeah, I don't have the equation written down.
My hope was that you have it in your head. Okay, good. Let's go to the equation. So we are counting up. See, we count up the index, the first index with n. Yeah, together with the x derivative, and we count up the second index with the y derivative. Right? Okay, so this is what we did here. We go one derivative in x, so we come from a equal, so from 1, 0, we come to 2, 0, and now we go in the y direction, and then we have what moment? No? 1, 1. Yeah, so we count up the second index with the y derivative. Yeah? Okay? Okay. Okay, so this to 0 order minus tau omega 1, 1 to 0 order. And there's no time derivative here because the time derivative would go second order again, right? So then obviously you can do the same thing for omega 0, 1. Omega 0, 1 to first order minus omega 0, 1 plus dx. Now we are counting up the first index. The first index is 1. It was 0, so it's 1, 1, 1, equilibrium 0, minus tau omega 1, 1 to order 0, and then dy. So starting from 0, 1, counting up the second index is 0, 2, equilibrium 0 order minus tau omega 0, 2 to 0 order. Okay? And now, as we have seen, this omega 0, 0 to 0 order, all the collision terms to 0 order are always 0. So we can leave it. We can actually leave it here because these things here, these 0 order terms, they will all disappear, and therefore our recursion has terminated. Okay, and with the terminated recursion, we can actually now write down exactly the equation that we're going to solve. Yeah? So this leads to 13.3, where we have omega 0, 0 to second order is equal to dx m10 equilibrium first order minus tau dx m20 equilibrium plus dy m11 equilibrium. Wait, I forgot the order. Okay, plus the y part, y m01 equilibrium to first order minus tau dx m11 equilibrium to 0 order plus dy m02 equilibrium to 0 order plus dt m00 equilibrium to 0 order. So, and this is the equation that whatever we do will be solved, and what we need to do now, the only thing that we need to do now is to decide what is tau and what are our equilibria. Yeah? So this is how we design our model. So we get to design the model. This is M00. M00 is conserved, or say it's a collision invariant, is M00 equilibrium is equal to M00. And this is, now we are designing the model, so there's no orders on this anymore, yeah, because this is what we actually do in the code. And in the code, we don't have the moments to a certain order, but we actually only have the moments themselves, right? So when this is a collision invariant, then this omega 0, 0, this is 0. And with this being 0, also its second order is 0. Then we observe that our equation that we want to solve does not have any first derivatives in it. Yeah? And we have the first derivative of the equilibria of the first order moments. So we find that if there is no first derivative, we need to put these guys here to 0. M10 equilibrium is the same as M01 equilibrium, and together this is all 0. And also there is no mixed derivative. So we have a mixed derivative, dx, dy on M11, and we have the same thing again, dx, dy dx M11, yeah, so this doesn't exist. So say that no mixed derivatives in our target equation. This means that M11 equilibrium is put to 0. Okay, so now we have decided what we don't have. Now we have to decide what we actually have. Namely, we want to have the correct second derivatives. Correct second derivatives. So let's do an ansatz. M02 equilibrium is equal to M20 equilibrium, which we put to theta. So we want to make it proportional because it should be there should be a derivative of C, and C is M00, right? So we put this proportional to C, so M00, and we'll have a constant that we have to specify. Let's then put this into the equation. This is dt M00, so I put this onto the other side. Hopefully. And let me see, there's a minus. Ah, yeah, right, so there's a minus, correct. And then I am left with dt into tau dx. No, what I'm sorry, it's not dt. Sorry. Dx, so partial differential to x, tau dx theta M00. Now also to zeroth order, plus dy tau dy theta M00 to 0 order, and this can be restated as nabla scalar product tau on nabla theta M omega 00. And okay, so this is actually the right order in which these derivatives are taken. Yeah, so actually on the theta, both derivatives are taken. On the tau, only one of the derivatives are taken. Yeah, and when they are constant, the way we often write the diffusion equation is we assume that these things are constant and we can put them in front. Actually, physically correct. So the nice thing with lattice Boltzmann is doing it physically correct. Yeah. So in reality, these things are in fact in this order. But now we could assume that tau and theta constant, and then we end up with dt M00, 0 is equal to theta tau Laplace operator on M00, and this to 0 order. And this means that d, our diffusion coefficient, would be theta times tau, which of course is, to be more accurate, is theta times 1 over omega minus 1/2. Yeah, if we want to implement it. So, are we done? Well, not quite, because we have not, I mean, we have our equation, that's nice, but we have not specified everything in our code yet, yeah? Because we also have moments that apparently we don't need. So what about the moments. So we started with D2Q9, so we'll have moments M21, M12, and M22. Now the observation is that we derived our model without considering them, meaning that they don't matter. Yeah? So they have no effect. No effect, at least in leading order. And because they have no effect, what we are going to do is we'll choose M21 equilibrium, M12 equilibrium. Let's choose them to be, they are asymmetrical things, so we'll choose them to be 0. And this M22 equilibrium, what we're going to do with this, we define a gamma. Gamma could be anything, and multiply it with M00. So gamma can, if you like, gamma can be 0 too. Right? Okay, we want to build an BGK model, so we'll have to deal with the so-called lattice weights that we get now out of our equilibrium moments. Okay, how does this work? So we have the definition of moments, MAB, the indices. So we are in D2Q9, so we'll have ij equal from -1 to 1 over I by the power of A and j by the power of B, and this into Fij. And when we want to solve this, we'll actually have to deal with the case that both A and I together can be 0, yeah, and in this case we define this as being 1. Otherwise, if we want to solve this, automatically we'll run into problems. So we solve this equation for the populations. So we know how to compute moments from populations, but what we need is populations from moments. Yeah? And for this, we can, okay, so we solve this, and then we get 9 equations. I try to write down the equations in a little bit more efficient way by using some parameters, lambda and sigma, which I say is not equal to 0, and say that f lambda, so lambda is the first index and sigma is the second index, so and they can be either 1 or -1, right? So and they got here 1 quarter m11 lambda sigma minus lambda m12, so the third moment minus sigma m12 plus m22. Yeah, maybe I should write this, that they are element in minus 1 and 1, right? So then we have the one where the second index is 0, and there we have 1/2 lambda m10 minus lambda m12 plus m20 minus m22, and of course the one in the other direction, sigma is 1/2 sigma m101 minus sigma m21 plus m02 minus m22. So does this make sense? Does it look similar to the other one with symmetry, I hope? And then there is there's one left with all 0, and this is m00 minus M02 minus 20 plus M22. So if we now know our equilibrium moments, we can compute the equilibrium populations. And then there's this lattice weights. So the lattice weights are basically the equilibrium these populations in the case that the density is equal to 1. So they are the populations at equilibrium and M00 equal to 1. So what we can say is that, for example, the weight 1 is M00 equal to 1/4 M11 equilibrium minus M12 equilibrium minus M21 plus what's the equilibrium? M22 equilibrium. So, what do we observe? We observe that this guy here, these guys here are 0, right? So this is what we said before. And this guy here is gamma M00. So this means for, say, if we choose gamma equal to 0, then this weight is 0. Is this nonsense? Okay, let's look. What does this mean? So we have this distribution here, D2Q9, yeah, and okay, not very well drawn now. And so there are, of course, the different weights. So, for example, here we have the weight 1, 0, and of course there's symmetry, so they will have the same here, and you have 1, 1, and 1, 1, the weights all over this place. So if they are 0, this actually does make sense. It just means we've reduced our lattice. So, yeah, we started with a bigger lattice, and what we end up with is this one. Yeah? Because we have vanished populations. Okay, what we just discovered, because there is no constraints on gamma. We can put gamma to 0 and we still solve our equation. We just observed that we do not need the 2Q9. We can also solve the same problem with the 2Q5. Okay, let's look at another one, M00W10. So this is the weight, that one is equal to 1/2 M10 equilibrium minus M12 equilibrium plus M20 equilibrium minus M22 equilibrium, and this is equal to 1/2 theta minus gamma M00. Okay, this, of course, W10 is, of course, the same as W01. Yes, all 1/2 theta minus gamma. Okay, one missing still is the 00, W00 is M00 minus M00 equilibrium. Okay, but okay, I guess I'll leave equilibrium out because equilibrium is M00 in this case, minus M02 equilibrium minus M20 equilibrium plus M22 equilibrium, and this can be combined to say that this is M00, 1 minus 2 theta plus gamma. Okay. Now there is another thing. We didn't put any constraints so far on theta. Now we said that potentially a gamma can be put to 0, and a theta could be put to 1/2, right? So if we put gamma to 0 and theta to 1/2, this means that W00 is 0. So does this make sense? Let's see. We'll have, now we just had this D2Q5. Now we are getting rid of the one in the middle, and we simply end up with D2Q4. Okay, so now, because there was no such constraint, we discovered that we can do this with only 4 speeds. And this would then mean that theta needs to be 1/2, and we'll end up with the equilibrium for these guys being, so they're all the same. They're just 1/4 C. And our update is Fij star is Fij plus omega Fij equilibrium minus Fij. And D is again theta times 1 over omega minus 1/2. In that case, that would be then 1/2, and this would lead to our equation dTc is equal to d c. So, and what we observe actually here is that, I mean, will this work? Yeah, this will work, this we know, because what we came up with is the same as forward in time central in space FD solver. Yeah, simply turned out to be the same. Okay, so we assume that it works. Okay, so this was as simple as possible. Now comes as good as possible, and for this, okay, sounds complicated, possible. How many is possible? 1 or 2? 2, okay, thanks. And here we use 2 relaxation times. Okay, let's do it this way. We assume 1 relaxation time which we call tau, and so there's a usual nomenclature, it's not my invention. Tau this is a small o, it's not a 0. Tau O, yeah? Tau O for odd, as in odd, and tau E as in even. So we split up our distributions or our moments in the odd moments and the even moments. And I guess you know what this means. So we have an order of a moment. So for example, the 0 moment, the first order moment, the second order moments, and the 0 and second and fourth, they are even order moments, and the first and the third, they are odd order moments. So we distinguish between the two of them. Now, the observation was that in our target equation, the relaxation acted on the first order moments. Yeah, so this is an odd order moment, and the others did not appear. So the only one in the target equation that actually bothers us is the odd relaxation. So actually, the equation looks like this. We have dtm00 to 0 order is tau odd theta and Laplace on m00 to 0 order. And the others don't have an effect on this equation. So now we can do whatever we want with the other one, in principle. Okay, so what do we want with them? There are several choices. Now we are looking at actually the most interesting one, which is to use it to improve our accuracy. Yeah, we could also use it to improve our stability or something else, but now we want to improve our accuracy. So, and this is by looking at the leading error. So how do we look at the leading error? We use our equation 13.2. We put A equal to 0 and B equal to 0, which gives us the equation that we want to solve. And the solution, we got our solution at second order, k equal to 2. And now the error, because we have a second order accurate scheme, the first error that we cannot ignore will come up at fourth order. Yeah? So we get the equation at fourth order. And when by doing this, we have to include a few assumptions, otherwise it would not work. I mean, not too heavy assumptions, just we have to build in the aliasing that M30 is equal to M10, otherwise it won't work. Yeah. And we'll also include already, but this is not really an assumption, we already include conservation on all orders, that this here is equal to 0. And we include all constraints gained at leading order. Yeah, they are still in here, of course. So they are already built in the equation. Yeah, I'm saying we include all of this because we want to simplify our thing as much as possible. Already, now this is 2D, this is not really very complicated, yeah, but already for this problem, it's getting quite involved, and here we actually require computer algebra to get the equation. So I will not present, I'll not present the entire calculation. So we put our equation 13.2 in the computer algebra system, give me the equation. Yeah? And with these constraints. So we'll have 0 is equal to omega 0, 0. Now we are talking forced order. Okay, and this has now the following terms that we observe. We have the time derivative of the equilibrium. Okay, I can skip equilibrium because here the equilibrium is the same as the moment itself. So, but to second order, yeah. So this actually is the error, yeah, because our solution is at 0 order. So this, the moment at second order is, of course, the. Okay, now I remember why I wanted to include this. I still write equilibrium here. Minus, to put some brackets, tau 0, theta, and here is Laplace M0, 0, equilibrium second order. And we'll call this guy here term 1, right? And then it goes on with tau odd times tau even times theta plus tau odd square theta minus theta 1/4 into dt Laplace M00 equilibrium 0. And now the important thing here is that this here is the solution. Yeah, so this is something that we cannot control. I mean, this is what we want to okay, say this here is term 2. And then the rest is tau odd theta by 1/6. So you see this is a result of a computer algebra. Yeah. Tau even tau times tau odd square times theta. And this now goes into forced derivative. So there's a forced derivative of M00 0 with or without equilibrium. Actually, and this, okay, it doesn't, I'm a little bit lazy here because it actually doesn't matter because equilibrium and the moment itself is the same. Yeah? dy forced order M00 to 0 order. And then we have a mixed term that is gamma. Gamma appears here, tau 0 minus 6, gamma t even, tau even and tau odd square, the x second derivative times dy second derivative. So it's a forced derivative, but a mixed forced derivative. And this goes into M00 to 0 order, which again is the original solution. And we'll call the rest here, all of the rest here we'll call term number 3. Okay, so now let's do some observations. Term 1 is exactly the diffusion equation again. So this is our original target equation. It just happens at the next order. And this equation can be put to 0 by appropriate boundary conditions to it, by appropriate initial and boundary conditions. So a diffusion equation with initial condition 0 and boundary condition 0 is also always 0. Yeah? So we can get rid of this quite automatically. So this is not a problem. unless it has source terms, and the problem is it has source terms. So 2 plus 3 together are the source terms in this equation. And they depend on the solution of the original problem, and the solution of the original problem is of course not 0, otherwise we wouldn't try to solve it. Now this is our problem because there's something that is not 0 and it's acting to produce, it's acting as source term for our error. So the target equation is, of course, the 0 order. Though they are not in general 0, so they are most of the time not 0. Not in general 0. So what to do? I've made a mistake here, but I can correct them. So, okay, let's briefly look back. Up here, we have in this term number 2, we have the time derivative of the moment m0, 0. And this is actually something that we know because this comes out of our target equation. Yeah, so we can obviously do a substitution here to modify our problem a little bit. So we have the time derivative of m00, yeah, to 0 order, and we can substitute this with the target equation. So what do we have? We have dt on Laplace m00 to 0 order. This is what we have. So we can rearrange this by taking the Laplace in front and have dt m00 to 0 order. And this will give us Laplace. So this is the right-hand side of the target equation. So it's Laplace of also of the left-hand side of the target equation. And we'll put this into our equation 13.5. Did I give this a number? Let me see. So this is the equation 13.5. Yeah, so we'll put this in here and we'll get to say, we'll recall this as 13.6. So there's a 0 is then dt m00, and now I don't write equilibrium anymore. Tau 0, wait, I guess I made a mistake. Oh dear, yes, I made a mistake. Sorry. Obviously there are no brackets. Yeah, so this acts on, yes. Sorry for that. Getting too confused. Okay, tau odd, theta and Laplace m00 to second order. Again, this is what we called this term 1, right? And then we now got a modified term, yeah, where you see now there is a Laplace on a Laplace. So we get, again, first order derivatives, and now we distribute this over our first order derivatives that we already have here. And now I've given similar lectures to this several times in several occasions in the world. And for whatever reason, every time I do this, I got this wrong. So hopefully today I got it right. And when you come up in an earlier version of a similar lecture, whether this comes from the ISMAS conference or on that channel here, hopefully now I've made it correct. Yeah. So tau odd equal to theta divided by 6 minus tau even tau odd square theta. So this is something that was here before. Yeah, and now we have to get the term due to this substitution. This is tau odd square tau even theta square plus tau odd. Okay, tau odd cube. So there's again a possibility to get it wrong. Because I mean, this is done by computer algebra. Yeah, it's not. I can't really check it while writing. Yeah. Okay, so this goes into the fourth derivative in x on the solution and the fourth derivative in y on the solution, and then we have the mixed term. Yeah, so we'll call this guy here A now. Yeah, and then we get the mixed term. So the mixed term goes then in gamma tau odd minus 6 gamma tau even tau odd square minus tau odd theta square half plus 2 tau even tau odd square theta square plus 2 tau odd cube theta 2. Okay, so no guarantee I get this wrong all the time. So if you really want to know and use it, do it yourself. So this is the mixed force derivative on M0, 0, and we're going to call this guy here B. Okay, now we have source terms. Now we actually basically got two source. Okay, we have three source terms with three different derivatives, but the prefactor of two of them is equal, and so we get actually two terms that are left, yeah, as source terms. And this 13.6, so the idea is that if the source terms vanish, the error vanishes, because there is no source of error anymore. Yeah? So this would give a null solution, meaning that this here would be identical 0 if A is equal to 0 and simultaneously B equal to 0. Yeah? And then the leading error would disappear. Okay, so meaning, and again, so there's a possibility that I get this all wrong here. Let me just try. So there's tau 0, tau odd times theta divided by 0 minus tau even tau odd square theta minus tau odd. So hopefully this is just the one above. By 4 plus tau even tau odd square theta square plus tau odd cube theta square is supposed to be equal to 0. And simultaneously, gamma tau odd minus 6 gamma tau even tau odd square minus tau odd theta square divided by 2 plus 2 tau even tau odd square plus 2 tau odd cube theta square is supposed to be equal to 0 at the same time. So now, how do we get these things to 0? There's physical things that we should not touch, yeah, because tau and tau odd and theta are there for defining our solution, our diffusion coefficient. So we are not supposed to touch them. So let's solve for the other two, because we have enough parameters. We solve for tau even, and we solve for gamma. And if we do this, we get tau even. Tau even is equal to 2 minus 3 theta plus 12 tau odd square divided by 12 tau odd 1 minus theta, and gamma turns out to be theta 1/3. Okay, I love this. Why do I love this? Because from the theory of cumulants, we know that gamma is supposed to be theta square. And usually in lattice Boltzmann, we derive that we should use theta is equal to 1/3, and this would imply gamma equal to 1/9, and this would actually be in line with the theory of cumulants. Even though we have to remember that the condition that we derive from the asymptotic analysis does not require us to put theta to 1/3 in this place. Yeah, it's just that if we put it to 1/3, we get this very nice result. So in this case, tau even is 1 plus 4 theta odd divided by 8 theta odd. So, and this is actually the result that you should use if you're trying to do this, but there's an earlier solution to this problem which is a little bit different and actually not quite accurate or not really correct, but is a good approximation for this. So it is. Let's do the following simplification. Let's assume that our diffusion coefficient is small, which we often have. So then tau odd is much smaller than 1, and then tau even is approximately 1/8 tau odd. And then we can define a quantity we call the magic number. This is actually its name. It's not a good name, but anyway. So lambda E odd, which is defined as tau even times tau odd. And this would then be 1/8. Yeah? Okay, so this here, again, this here is the approximation, this here is the correct one. Yeah? So, the thing is, it has been known for 20 years, more or less empirically, that you get much better results if you use by using two relaxation rates that we put them to 1/8. Yeah? Why? Because this is an approximation to the solution that would turn your model first order accurate. Putting it to 1/8 is not first order accurate because you still have an error of first order, but this error is small. Yeah? Okay, so actually you should forget about this and you should use the right solution. Just to wrap up a few things that I've written down. So particular behavior of LBM is often seen for, so in other cases this result could be different. For example, in the Navier-Stokes equation, this would probably be different. But we see usually interesting results if this odd-even number, lambda odd-even, is made constant, and this has given rise to its name as magic parameter. So if you put this to a constant, yeah, and you choose, you have to use one relaxation rate. In the Navier-Stokes equation, it's the other way around. Yeah, so it's the even rate that defines the viscosity, and then you have to choose the odd rate so that the product of the two is this constant or a different constant. Yeah, then you get an interesting behavior. In that case, we can actually eliminate the leading order error and causes this model to be first order accurate, at least theoretically. Now it's up to you to prove me wrong. So it's first order convergent. Of course, only if you use appropriate initial and boundary conditions, yeah, because they were excluded from the analysis. And the interesting thing with these magic parameters is that they come for free, yeah, because so you don't need to use a larger stencil or whatever. Of course, you have to use, now, okay, it's not quite correct. You have to use a larger stencil than the minimal stencil that we found. Yeah? In that sense, it's more expensive, right? But starting from the D2Q9 lattice, it does not cause any overhead because it is just a rearrangement of operations and no additional operations. Okay, so this, I hope I got it right this time. So this was this advanced lecture, which also concludes the series, the usual series of this, so the usual lectures, yeah, or the normal lectures. So we'll have one more meeting next week, for which I have to still make a plan, but the lectures are now finished. So thank you for attending. See me.